Hi everyone. So in this video, we're basically going to be continuing to talk about the same ideas from yesterday's video, but we're going to have some new notation and new vocabulary to talk about these things. So specifically, we're going to be focusing on, again, finding the area bounded by a function. So the new notation that we're going to use for describing this kind of area bounded by a function is something that's called an integral. And so it's going to look like this. We're going to write down this kind of, it basically looks like an S, but very much elongated. And then there's going to be two numbers, one at the bottom and one at the top. So we typically will use A and B to represent those two numbers. And then you have your function, and I'll kind of explain what that function represents in a moment, but you have some kind of a function. And then at the end, you have dx. And so one thing I just want to point out is that basically whatever variable you're using in your function, so whatever variable you see here, you need to see that same variable appear here. So for example, instead this could be like f of t dt, or f of w dw, or f of y dy. It doesn't really matter what variable you're using, but you do need to ensure that the variables match. So what does this symbol mean? So this basically means, and actually first let me write down how you would like read this out loud, and then I'll say what it means. So the way you would read this out loud is you would say the integral of f of x from a to b, or you might say from x is equal to a to x is equal to b. So this means the area between f of x and the x-axis bounded by x is equal to a on the left and x is equal to b on the right. So I'm going to draw kind of a general picture here, and we'll see there's one more kind of detail I need to add to this definition, but I'm not going to add it just yet because I want to do some simple examples first, and then we'll come back and kind of add in that one other complication. So basically, let's say that you have some kind of a function, and let's say that you have an x value here that's a, and an x value here that's b, and this is your function f of x. So if you take the integral from a to b of your function, that just means that you're finding the area enclosed between a and b. So a is on the left, b is on the right, and then between your function and the x-axis. So you would be looking at this area here. So that area would be the integral from a to b of your function dx. So as we saw in yesterday's video, there's only certain types of functions where we actually know how to compute that area perfectly. So in a lot of the cases, at least for now, if we're computing an integral, we're actually going to be approximating it using rectangles. So in this video, we'll do kind of both examples. We'll do some examples where, because of the type of shape we're dealing with, because of the, if we're dealing with like a graph of a line or some other kind of a shape that we actually do know how to find the area, that we'll be able to find the exact area. But in a lot of cases, we'll still need to use rectangles to approximate. So yeah, bottom line, really there's not much new going on yet. It's just this new symbol. It's just a new way, instead of always having to write, find the area bounded by this and bounded by that, we now have this symbol that kind of summarizes that idea all in one. So just to give a couple of examples, and these are ones that we already did yesterday, but I want to kind of rephrase them in terms of integrals. So this one was one of the first examples we did yesterday. So this was the area. The way we said it yesterday was we said we're finding the area bounded by f of x is equal to 3 and the x-axis between x is equal to 0 and x is equal to 4. And so the way we would write this as an integral is we would say the integral from 0 to 4 of 3, because that's our function. And then you have to always put this dx on the end. So it's really, really important. Like the way that I would kind of think of it, and we'll talk more in tomorrow's video about what this dx means and where it comes from. But the way that I like to think about it is I like to think of this and this as being kind of, it's almost like they're parentheses. They go together, and then you put your function in the middle of those two. So we found yesterday, and we can find it again just looking at this picture, that this area is equal to 12, right? Because you just do base times height. So the integral from 0 to 4 of 3, the function f of x is equal to 3, is equal to 12. So another example we did yesterday was this one. So this would be the area bounded by, so this function was f of x is equal to negative x plus 5. And maybe let me just put that same up here. I'll say here, this is f of x is equal to 3. So in this picture, or in this example, we're taking the integral from 0 to 5, because the 0 is where we start on the left, the 5 is where we end on the right. And the function that we're integrating is negative x plus 5. And so if you have a function that involves addition, technically you're supposed to put parentheses around it. You'll see that, I think in our book they do that. I will probably forget sometimes. A lot of people don't put the parentheses, but I'll try to put them. It's basically just, again, it's because this dx kind of has to apply to everything. And again, we'll get more into that in tomorrow's video. But for now, just remember that technically you should really be putting parentheses if you have addition in your function. But it's, if you don't put them on like a test or quiz, I'm not going to take points off. It's not a super big deal. So in yesterday's video, we found this area by doing base times height over 2, and we found that this area was 25 over 2. So in the language of integrals, the integral from 0 to 5 of negative x plus 5 dx is equal to 25 over 2. So one last example. So this was the function f of x is equal to x squared. So this is one where it's a curved shape, so we can't actually find the exact area yet. But I told you what the answer was, and we also kind of figured out what the answer was using rectangles. And then remember, we went into Desmos and we really increased the number of rectangles to the point where we could get a much better idea of what this area is. So in this case, we would be doing the integral from 0 to 3 of x squared dx. And we figured out basically that area was equal to 9. So one thing I just want to emphasize here, because I think if you've taken Calc 2 before, or even sometimes in Calc 1, you actually see this symbol, this integral symbol, you might have some idea of the relationship between integrals and antiderivatives. If you already are aware of that relationship, you don't want to be thinking about it right now. If you have no idea what I'm talking about, that's totally fine. But if you already know about this relationship between the integral symbol and antiderivatives, don't be thinking about that relationship right now. Right now, we're literally just thinking about areas. So we're either using rectangles to estimate an area, or we're finding the exact area because we can just use geometry formulas. So we're not doing anything involving antiderivatives right now. So one other detail I need to add to this that I didn't say is that notice that all of the examples that we did, all the graphs lay above the x-axis, right? So all of these graphs were above the x-axis. But you can take an integral of a function that actually dips below the x-axis as well. So let's say that I'm going to kind of just scooch this over here, and instead of having b be this number here, I'm going to move b to be over here. So how would that work if you were taking this integral? Well, basically, you would still be finding areas, but the distinction that needs to be made is that any area that lies below the x-axis is actually going to be counted as negative. So you would basically add up, and again, we don't yet know how to find this exact area, but you would figure out what is the area that lies in this part above the x-axis, but then you would need to separately figure out, what's this area that lies here below the x-axis, and that would be counted as negative. So we'll see a couple of examples of this in today's video, but the important thing is that anytime you're doing an integral, you're always looking at the area between your function and the x-axis. whether your function's above or below the x-axis, you're always just kind of going either down or up, looking at that area between your function and the x-axis. If that area lies above, then it's counted as a positive area. And if that area lies below, it's counted as negative area. So let me just kind of summarize that in what I wrote up here, which is if f of x lies above the x-axis, the area is counted as positive. If f of x lies below the x-axis, the area is counted as negative. Okay, so the first example we're going to do is going to be one where we have to use rectangles to approximate, and then in the remainder of the video we'll do some examples that are kind of like these ones. So examples where you can just use geometry, you can use triangles, rectangles, we'll see some semicircles, things where you can actually just find the area without having to use any approximation. So the first example I want to look at is we are going to, sometimes these get stuck. Okay, there we go. So first example we're going to do is we are going to approximate the integral from 0 to 3 of negative x squared plus 4 dx. And we're going to use R6. So remember, R6 means that when we draw our rectangles, we're going to be using the right endpoint of each rectangle to determine its height. And then this number 6 means that we're using 6 rectangles. So our first step is that we need to actually draw our function and kind of figure out what are we talking about here. If we're taking the integral from 0 to 3, what does that region look like on our graph? And once we have that region, then we can start putting in the rectangles and using that. So what does negative x squared plus 4 look like? It's an upside down parabola that's been shifted up by 4, right? So its vertex is at 0, 4. And then it's going to, if you kind of know what the shape of a parabola looks like, it's going to go like this. And then it's going to keep going down. So if you plug in 3 to negative x squared plus 4, you get negative 5. So that means that at 3, it's going to be all the way down at negative 5. And that's really as far as we need to know. So what is the area that we're looking for here? We're basically looking for this area. And then we're going to add that to this area, but we're going to be counting this area here in red, we're going to be counting that as negative. And so we're going to be using 6 rectangles to try to approximate this area. So let's see, maybe I'll use dark green on this positive part, and then I'll use like orange or something on the negative part. So we want to divide, because we're looking for 6 rectangles, that means that we need to divide each of these 1, 2, 3, we need to divide each in half. So we're going to have a point at 1/2, another point at 3/2, and then another point, and maybe actually, sorry, I'm being a little fixated on color here. I'm just going to do that in black actually, so that it's a little more consistent. So 1/2, 3/2, and then 5/2. Okay, so for our first rectangle, we're going to use the right end of our interval. So that means that the height is going to be determined by 1/2. And again, sorry, I didn't really draw that very well, so I'm just going to make that a little better. Okay, so that means that we're going to have a rectangle where the height is determined by f of 1/2. So this point here is going to give us our height. So that's going to be our first rectangle. Our second rectangle is going to have a height determined by 1. And so that's going to be here, like this. Our third rectangle is going to have a height determined by 3/2. So that will be, if you plug in 3/2, let's see, that's going to be like here. And then our fourth rectangle is going to have its height determined by the right endpoint, in this case is 2. And so 2 has an output of 0. And so that's going to be one of those rectangles that just doesn't have any area. So if the endpoint you're using is at a height of 0, then you just don't get a rectangle for that part. And that's fine. You know, you can tell that that means it's not going to be super accurate, but you know, we're just trying to approximate. And then for the rectangles on this other part, so we just do the same thing. So we still are using the right endpoint. So when we get to 5/2, that's going to put our right endpoint somewhere like here. So we're going to get a rectangle that looks like this. And notice that it's kind of a little too big, right? It's covering up some of the function, but that happens because we're approximating. These are not going to be perfect. And if you notice in the first part, the rectangles are all a little too small. In the second part, the rectangles are a little too big. And that's just kind of how it works out. And then the last rectangle, we're using, again, the right endpoint. So we go down to the output at 3. So that's here. And so we get this rectangle here. Okay, so how do we find this area? Well, we're basically just doing base times height, base times height, base times height, and adding all of those up. And because the heights are negative for these ones in purple, we can still do base times height, and that will have the effect of subtracting them, right? Because if we do, yeah, like I guess height isn't quite the right word, but if we do the base, so the base for all of these is 1/2, right? Because that's the width of these rectangles. If we just do 1/2 times the output times the y value of that point, then the negative ones will automatically be counted as negative. And so we'll get this balancing act where the positive part will be positive, negative part will be negative, and some stuff will cancel out. So I mentioned this in yesterday's video. Rather than saying base times height, base times height, base times height over and over, we can factor out the base because it's the same for all of them, right? All of them have a base of 1/2. So rather than do 1/2 times this plus 1/2 times that plus 1/2 times that, we can factor out the 1/2, and then all we have to do is add up the different heights. And so where are those heights going to come from? Well, the first one is going to be f of 1/2. The second one is going to be f of 1. The third one is going to be f of 3/2. The fourth one is going to be f of 2. Then we have f of 5/2. And then finally we have f of 3. So we're just adding up all of those different heights. And so if you type these into a calculator with the function, remember, is negative x squared plus 4, you'll find that f of 1/2 is, and I guess I wrote these as decimals. I usually like to use fractions, but I guess I wrote these as decimals, so that's what I'm going to write down here. So we have 3.75 plus 3 plus 1.75 plus 0. That's the rectangle that doesn't have any area, right? That's the one that was like here. And then f of 5/2 gives us negative 2.25. And then the last negative one is f of 3, and that's negative 5. And so if you do all this out, multiply by 1/2, you'll find that this total area is going to be 0.625. So that is our approximation. And so the reason that, this is kind of a small number, right? I guess what I want to emphasize is that if we had done the integral instead from 0 to 2, we would have gotten a bigger result, right? Because the integral from 0 to 2 would be all just positive. But because we have this negative part, it's kind of counteracting the positive part and kind of canceling it out. And so that's why we're left with this smaller result. That being said, this is actually not a very accurate approximation, and I'll show you a more accurate one on Desmos, and we'll see what the actual area is. I'm not sure exactly why it happened in this case. I think maybe just because of how steep the graph is on this second part. I think the rectangles are just a little too much bigger than the graph. But let's look at the picture here. So this right now, what we're seeing here is what we had, right? We have 6 rectangles, and we can see that we have one of them that has 0 area. So if we look at, so see this kind of funny equation here, we'll talk in tomorrow's video about, where this stuff is coming from, this weird giant symbol. But this number here where it says I is equal to, that's telling you the total area. So if we increase the number of rectangles, let's keep an eye on what's happening to this area and see kind of where it's going. So I'm going to increase it to, let's first do 12 rectangles. Now it says that the area is 1.84 approximately. And I'm just going to keep increasing it. And remember that the more rectangles we have, the more accurate the area gets, because it's starting to really kind of mimic the shape of this graph. And so the highest this goes is 100. And you can see that we get 2.86455. And so the actual area, and when I say the word area, by the way, that it's not quite correct to say the word area, because the word area is meant to only mean positive things. Here we're talking about area that could be positive or negative. But anyway, the total area, if you add up the positive green stuff and the negative red stuff, it actually is 3. So our approximation really wasn't that good. That's fine, it's an approximation. But just so you know that this rectangle method works better for some functions than others. And even if we had done 12 rectangles, our approximation still wouldn't have been that good. So just kind of keep in mind that because, rectangles are boxy and curves are curved, you're not really getting a shape that is very accurate unless you use a lot of rectangles for some of these functions. Okay, so that's approximating. So again, approximating works exactly the same as it did in yesterday's video. It's just that when you have these rectangles that are below the x-axis, you have to count them as negative. Now we're going to do some integrals where we actually can find the exact value because of just using area formulas. So first example I want to do is we're going to find, sorry, I'm just pulling up my notes. There we go. So we're going to find the integral from 1 to 4 of negative 2x plus 4 dx. So the first step is to actually graph our function, and then we will figure out what part of that function are we actually talking about, and then we'll find its area. So negative 2x plus 4, that means we have a line with a y-intercept of 4 and a slope of negative 2. So it's going to look something like this. And we're doing the integral from 1 to 4. And so that means we're starting here and ending here. So the area that we're looking at in this picture is going to be this area here. And then this area down here will be subtracted. So one thing I just want to point out is just based on this picture, I want to kind of pause and let you think about this. What do you think will be the sign of our answer? Do you think the integral from 1 to 4 of this function is going to be a positive or a negative number? So it's going to be negative, right? Because we can just tell from this picture that the red portion is way bigger than the green portion. And so it's definitely going to outweigh it. And we'll see that when we actually find the areas. So what is the green area? Well, again, the way that you find the area of a triangle is you do base times height over 2. So the green area is going to be, the base is 1, the height is 2, and so that gives us 2 over 2, which is 1. So we have an area of 1. And then the red area is, again, if we do base times height over 2, the base in this case is 2, the height is 4, and then divide that by 2, and we get 4. And so our final answer is going to be 1, that's the positive part, minus 4, because that part counts as negative. And so our total answer is negative 3. So the integral from 1 to 4 of negative 2x plus 4 dx is equal to negative 3. All right, another example. So in this one, we want to do the integral from negative 3 to 3 of the square root of 9 minus x squared dx. So this might, initially not be something that you really know what the graph looks like, but this is one that We'll see this type of integral actually come up a decent amount. So this is a type of equation I want you to get familiar with. So what's the deal with square root of 9 minus x squared? Well, if we were to write this as y is equal to square root of 9 minus x squared. Let's say that we were to square both sides. So we would get y squared is equal to 9 minus x squared. And so if we then add x squared to both sides, we get x squared plus y squared is equal to 9. So that would be a circle, right? That would be a circle centered at the origin with a radius of 3. However, the actual function we're dealing with, y is equal to square root of 9 minus x squared, that's not the whole circle, that's just the positive part of the circle. Because if you were to kind of reverse this, if you were to start with the circle equation and try to solve it and get this, you would actually have a plus or minus. Because when you would take the square root of both sides, you get a plus or minus. So when you have a positive square root, that is the top half of a circle, so it's a semicircle and it's the positive half. If we had a negative sign out front, then that would be the bottom half of a circle. So I want to kind of write that down here in general because that's a good type of function to be able to recognize. So f of x is equal to the square root of r squared minus x squared is a positive, actually let me just say it this way, is a semicircle of radius r, so whatever number, so in our case we had 9, right? So the radius ended up being 3, centered at 0, 0. And so because it's positive, it's the top half of the circle. And then if instead you had the function negative, so a negative sign outside, square root of r squared minus x squared, that is also a semicircle. I guess I could have written this in a way that was more concise, but that's okay. So it's also a semicircle of radius r centered at 0, 0. And that would be the bottom half. So I'd really recommend that you in the same way that hopefully at this point you're familiar with a lot of kind of basic functions like lines and, simple exponential functions and parabolas and all the types of graphs that you hopefully kind of just know what the graph looks like without having to make a table. I would add this to your mental list so that when you see a function that looks like this, you know that it is a semicircle. Okay, so why is this useful? Well, if our graph is a semicircle, so I'm just going to erase this and write that in here. So this is a semicircle of radius 3. So if our graph is a semicircle, that means that we'll be able to use the circle area formula to find its area. So the area that we're looking at in this picture is this area here. And it's all above the x-axis, so it's going to be positive. So the area of a circle is pi r squared, right? So the area of a semicircle is half of that. So we want to do pi r squared over 2. So if we do pi times, the radius was 3, so pi times 9 would be pi r squared. Maybe I'll even write it like this just to be a little bit more suggestive. So pi r squared divided by 2, and so that is going to be 9 pi over 2. And that is our area in this case. So just kind of a heads up, I feel like a lot of students kind of forget that we're just talking about areas here. So if you were to, maybe if this question was on the homework or something and you were just to type this into Google, it would actually tell you a different way to do it using methods that we're not going to learn for like weeks. And so if it was on a quiz and I put this and I saw that answer, that method show up, I would know that you were cheating. So make sure that you're kind of paying attention to what are the methods we've learned so far, because I think that's an issue that will come up in this class a good amount, is that there are kind of beginner methods for a lot of these integrals, and then there are methods that are more advanced that we'll learn later on. And it will be very obvious to me if you're using methods that we haven't learned yet in the class. So for now, again, we're not doing anything with antiderivatives. We're just finding areas using geometry formulas. Okay, one last example for this video. And at first, this might seem like one that is going to be hard to find using geometry, but we'll see that one thing that's really useful in this class is going to be taking advantage of symmetry. So let's try to find the integral from 0 to 2 pi of sine of x dx. So hopefully you remember what the graph of sine and cosine and those basic trig functions look like. So sine of x is going to start by going up, and it's going to go back through the x-axis at pi, right? So it will hit its highest point at pi over 2. So the beginning of it will look something like this. And then the second half is going to go down to a height of -1 at 3 pi over 2, and then it will hit back at 0 at 2 pi. So I'll just quickly say this again, I really would expect in this class, as we move forward in this class, there's definitely going to be cases where you're going to be expected to be able to graph things like sine of x or negative x squared plus 4, any kind of like simple function. I'm going to expect that you know what the graphs look like and that you can graph them by hand. So that's something that, if you know that you're a little rusty on, you might need to take a little time to just brush up on. And I would recommend looking at that pre-calculus review that I put in on Canvas. Okay, so what is this area going to be? Well, without actually calculating the area, let's just kind of shade in what's going on here. So we have a positive region up here, and we have a negative region down here. And these are not shapes that we know how to find the area of, right? They're not circles, even though they're round. They're not triangles. We could use rectangles to approximate, but we're trying to find the exact area, right? I didn't tell you to approximate. I said, find it. So it turns out that it doesn't really matter exactly what this green area is or exactly what this red area is, because all that matters is that they're equal to each other, right? The sine graph is very symmetric. So basically, the green area is going to be the same as the red area. And so basically that means that they cancel each other out, right? Because the green one counts as positive and the red one counts as negative. And that tells us that the value of this integral, the integral from 0 to 2 pi of sine of x dx, is equal to 0. All right, so that is it for this video. Like I said, in the next video, I will be going over something called summation notation and seeing how, like, a little bit more detail about where this dx comes from, basically just getting a little bit more technical about this integral symbol and what exactly it means. And yeah, and today's worksheet is going to give you some practice with, again, both using rectangles to approximate and finding exact areas in the situations where that is possible. All right, I will see you all next time.